Welcome. In this video I'm going to be continuing to look at scanning tunneling microscopy or microscopes, STM. So there's already two videos in this series and there's links to them up above. Please check them out. So in those two videos we looked at how STM can be used to look at atom positions and image the surface, and we also looked at how STM can be used to do atomic manipulation and move atoms about. So the question is, why isn't this technique more widely used and more commonly used and known about? What are the issues with it? And this is what I'm going to address in this video. So, first of all, STM relies on measuring tunneling current to do the imaging and also to be able to pick up the atoms, which means that your sample has to be conducting or semiconducting. So this is one of the limitations of STM, that you need a conducting substrate and sample. The second main issue of this, and if you look at this image here, this is the STM that I use, that it's in a what's known as a UHV chamber. So this is a system where the pressure inside these sort of metal bubbles is a billion times lower than atmospheric pressure. And the reason why we have to carry out STM, well, we don't have to carry out STM in ultra-high vacuum or in vacuum, but for the best results we do, is because we're very interested in the surface of the material. And the surface of the material is very susceptible to being contaminated. So there's carbon, there's moisture in the air around us, which can form a thin layer over our sample. And if we're trying to pick up atoms or look at atoms on the surface and where they are, any couple of layers of other materials such as water or moisture or any other contaminants is going to affect our ability to be able to see those atoms underneath. So we need to clean the sample, and once it's cleaned, keep it clean. So this is why we have to do it in ultra-high vacuum, because that removes the moisture. It also removes any carbon contamination. So an STM system will normally have a chamber on it where you can actually do your sample prep and clean your sample. This can involve snapping a sample in half to expose a clean edge. It can involve heating to evaporate the moisture. It can involve argon bombardment, which is effectively sandblasting your sample with argon atoms just to remove that contamination. So you need to make it very clean. The third problem we also have is the actual material itself. To be able to STM, we need to have a very good order of the atoms, otherwise we're just not going to be able to see it. Remember, we don't actually look at the atoms themselves, we look at the electron clouds around it. So you need a good order of atoms in your substrate, otherwise your electron clouds tend to overlap and form other sort of superficial structures over the top, which your tip will then move over and you get like a cloudy-like image. So this is something that you might see when scanning gold, such as this image above. You don't actually see the atoms, you just see the sort of general electron cloud. Another problem we have is the tip. We want the tip to be as sharp as possible to be able to pick up where your atoms are, because you need to know where your tunneling current is flowing to and from. So to make the ideal tip, we have to etch them out of tungsten. Again, tungsten oxidizes, so once you've made your tip, you need to put it into your sample, have another chamber which is suitable for cleaning that oxide off the tip, and you need to keep it very sharp, so you don't want the end of that tip to touch the sample. You always want to keep it suspended above the sample. So again, this can pose some issues. Another major problem is mechanical stability. Any small vibration on the atomic scale or any macro scale vibration, such as vehicles going past the lab, vibrating the floors, lifts going up and down, these small, what we would consider quite small vibrations, are large on the terms of atoms. So again, this can really affect your image quality and how difficult it is to do the measurements. So these STM machines have to be sat on special foundational concrete slabs to minimize these vibrations. There are damping systems within the machines themselves to using springs and magnets to try and reduce any movement. Also, the whole system will float on air legs, again to decouple vibrations that can be moving from the outside environment. So these make these techniques tricky to carry out. It makes them expensive to carry out, and this doesn't really address when you're trying to make machines that operate on atomic precision. It's expensive to do, it's tricky to do. So these are the reasons why STM isn't widely used. There are other techniques that can gain similar information which require less cost and less time and less effort. So STM is a very good technique, and there are still science to be done using STM, and they can be very powerful tools for gaining information on materials. However, this is one of the reasons why over the past 40 years since STM was created in 1981, why it hasn't really become sort of a common foundation in all of science. I hope you've enjoyed this video and you find it informative. Please check out my other videos. If you do like this video, hit the thumbs up icon. Also hit the subscribe if you want to subscribe to my channel.